Okay, so still in section 2.6 here, we're going to do another example of a limit as x approaches infinity. This one looks a little bit different. The previous two examples that we did involved quotients, functions that were defined as quotients. This one is not a quotient, but if you try to think about it intuitively, it's a little hard to see what is going on here. So think about it this way. This first expression here, the square root of x squared plus 1. As x approaches infinity, we're thinking of x as becoming an arbitrarily large number. So imagine plugging in very, very large numbers for x. We square it, which gives an even larger number, add 1, even larger, take a square root, which will make it smaller, but still a very large number overall. As x gets bigger and bigger, this entire expression is going to be getting bigger and bigger, and it's going to be approaching infinity, which again, remember, there's no such thing as approaching infinity, but we use that terminology anyways. Now this x here, as x gets larger and larger, this is just x, so this is the same number that we're plugging things in for, so this is going to be approaching infinity as well. And we get something that's called, that looks like infinity minus infinity. What is infinity minus infinity? Well, it's not 0, not necessarily. Remember, infinity is not a number. So even though it's tempting to look at that and say, well, that's just like doing 2 minus 2 or 100 minus 100, isn't it 0? Not necessarily. Infinity is not a number, so it doesn't behave the way other real numbers work. And it's unclear exactly what this would be. So we have to handle this limit a little bit differently. Here's what we're going to do. We're going to take the limit as x approaches infinity. Here's the expression that we're working with. Square root of x squared plus 1 minus x. Technically, I actually should have had parentheses here as well. We're going to multiply this by an expression that's equal to 1 using the conjugate of this expression. If you remember, we've talked about the conjugate before. The conjugate of this would look like x squared plus 1 plus x. And I'm putting it over itself, x squared plus 1 plus x. Okay, now when we do that, this is being multiplied to the numerator here, and I have something that looks like a factored version of a difference of squares. So the end result is going to be this thing squared minus this thing squared, at least as far as my numerator is concerned. Limit as x approaches infinity of, well, the square root of x squared plus 1 squared is simply x squared plus 1 minus x squared over the square root of x squared plus 1 plus x. Okay, I can see these x squareds canceling out now. And I get this, 1 over square root of x squared plus 1 plus x. Okay, now this thing is equivalent to what we started with, but it's in a more usable form. So now that I've put this in the form of a rational expression, or a quotient is a better word for that, I see that I have a numerator that's constant, a 1. My denominator looks similar to my original expression, but I'm no longer subtracting two very large numbers, I'm adding them. And so the limit as x approaches infinity, again, remember each of these expressions, this big radical expression and this x here, are both approaching infinity as x approaches infinity. So we think of that as a very large number here, very large positive number here, plus another very large positive number here. The end result would be another very, very large positive number. So what we're seeing is a denominator that's getting larger and larger as x approaches infinity, which means the overall fraction is getting smaller and smaller in the sense that it's tending towards 0. Okay, now I think I did say that in this case infinity minus infinity is not 0. We happened to get 0 out of our answer here. Other cases might give you something other than 0, and again, that's sort of more reason to not assume that something like this works the way that you expect it to. Okay, but you have to use little tricks like this when you're evaluating these kinds of limits. Now I'll do a little I guess foreshadowing for, not foreshadowing, but a little preview of something that we're going to talk about in chapter 4. These types of limits where you write something like this, infinity minus infinity, this expression takes what we call, or this limit takes what we call an indeterminate form. And indeterminate forms, we have another more wide-reaching way of dealing with these types of limits using something called L'Hopital's rule. But again, that's all the way in chapter 4 where we revisit these types of limits. All right, let's go ahead and move on. All right, up here I have this little explanation that we're going to use to evaluate a couple of limits. It says, in some cases, it's helpful to make a variable substitution when evaluating a limit, whether or not it is a limit at infinity. So let's take a look at this one. The limit as x approaches 3 from the negative side of this expression, 4 over x minus 3. Okay? Now you could try and deal with this directly, but obviously you can't just plug this 3 in here because you're going to end up dividing by 0 if you do that. So what we're going to do instead is we're going to make what we call a variable substitution. I'm going to set u equal to 1 over x minus 3. Okay? And actually, in this case, I don't even know that we need to do that. Let me see. I guess we could. Yeah, we can do that. So that doesn't change this by a whole lot. But what I'm going to do is say what is happening to u as x approaches 3 from the left. Okay? So u is going to be approaching what? Well, if x is approaching 3 from the left, remember we're using numbers that are smaller than 3 to to approach 3. So 2.9, 2.99, 2.999, and so on and so forth. So that means this x right here, if I'm doing this numerically, is always going to be smaller than 3. So if I subtract 3 from it, it's going to be a negative number. Okay? So as I approach 3 from the left, every number that I would use to do that is going to give me a negative denominator. And the reciprocal of a negative number is still a negative number. So u is going to be a negative something, right? But not only that, what's happening as x is approaching 3? Well, I'm getting a very small denominator in the sense of being close to 0. So it's going to have a small absolute value. 2.9 minus 3, for example, that's negative 0.1. 2.99 minus 3 is negative 0.01, and so on and so forth. 1 over a denominator that's very, very close to 0 is going to be a number with a very large absolute value, meaning it's either a really big positive number or a very small negative number. But we've already decided that it's negative. So the logical conclusion here is that u is approaching negative infinity as x approaches 3 from the negative side. Okay? Now, in fact, I made this 1 over x to the 1 over x minus 3. I actually don't even really need to do that. I can make it 4 over x minus 3. I'm not sure why I went with the 1. The 4 is what's already appearing there, so we might as well just grab the whole thing in here and set u equal to that. Now what we're going to do is make a variable substitution. Anywhere in this limit I see an x, I'm going to be replacing it by the appropriate expression involving a u. So again, as x approaches 3 from the negative side, u, the way we've defined it, is approaching negative infinity. So this is equal to the limit as u approaches negative infinity. Notice I've changed what the limit looks like because I'm using a new variable now. The argument here on my inverse tangent function is u. So this becomes the inverse tangent of u. Okay? Now we have seen the graph of the inverse tangent function in this section already. We saw it right here. Okay? So as our independent variable, we're calling it x here, we're calling it u here, but aside from the labels, the graphs would look identical. As x approaches negative infinity, our inverse tangent function has a horizontal asymptote that it's approaching, negative pi over 2. And again, doesn't matter that we're calling it u here, this would do the same thing. This is approaching negative pi over 2. Okay? So one example where a variable substitution is a nice one to use. Here's another example. We want to compute the limit as x approaches 0 from the left of the function e to the 1 over x power. So in this case, I want to start by looking at y equals e to the x, which we call the exponential function. And specifically, I'm interested in the graph of this function. You should know what the graph of this looks like. It's an exponential function. It looks like this, right? Very roughly, right? Now, one thing I know about the exponential function, it does not have a horizontal asymptote that has any impact on the graph as x approaches infinity, but it does have a horizontal asymptote as x approaches negative infinity. You can see that the graph is going to be approaching the line y equals 0, right? So this has a horizontal asymptote at y equals 0, and it only affects what's happening to the graph as we approach negative infinity, as x approaches negative infinity. Now here's an exponential function, or it's a composite function involving an exponential, and it's very similar to this. What I want to do is make a variable substitution that'll allow me to refer to this graph. So once again, I'm going to set u equal to something, but in this case I would want to set it equal to the thing I'm seeing in my exponent, 1 over x. Okay? Now, what is happening to this expression? What is happening to u as x approaches 0 from the left? Well, again, if we're approaching from the left, that means we're using numbers that are less than 0. That would make them negative. So we're approaching 0 using negative numbers. Positive over negative is negative, so we're expecting u to be approaching a negative number. And in addition to that, just like the previous example, if my denominator is going towards 0, but my numerator is a positive number, or not a positive, but a constant, then a constant numerator and an ever decreasing and ever smaller denominator means that this whole expression is either going towards infinity or negative infinity. In this case, it would be negative infinity because we decided that this should be negative down here. So then u is approaching negative infinity as x approaches 0 from the negative side. So now making those substitutions, I can rewrite this as the limit as u approaches negative infinity of e to the u. But again, the u is just a label. The graph of e to the u is the same as the graph of e to the x. It's the same thing. And as we approach negative infinity, we know that there's a horizontal asymptote here. This should be approaching 0. Okay? So another example where a variable substitution was helpful. Okay. Now, so far we've been looking at limits as x approaches infinity or negative infinity, specifically in the cases where our function, when graphed, has a horizontal asymptote. But as we already know, lots and lots of functions don't have horizontal asymptotes. Think of a parabola as an example. Parabolas, whether they open upwards or downwards, are not approaching some finite number as x increases towards infinity or decreases towards negative infinity. It just skyrockets up to infinity itself or down to negative infinity. So in those cases, you're going to see the infinity plus or minus show up in 2 places. So if a function f of x does not have a horizontal asymptote as x approaches infinity, then we're going to get one of these 2 cases. F of x either goes towards infinity or it goes towards negative infinity. Similar for cases where x is approaching negative infinity. We might have one of these 2 cases. So here, we want to evaluate the limit as x approaches infinity of the function x to the 5th, or the limit, and the limit as x approaches negative infinity of the same function. Okay, from what you know about polynomials, you should know that they never have horizontal asymptotes. Never. So each of these should be either positive or negative infinity. We determine which one by either looking at the graph of the function y equals x to the fifth, or just by using some kind of basic knowledge of exponents. So think about this first one for a second. The limit as x approaches infinity of x to the fifth. Again, when x is approaching infinity, we're imagining plugging in larger and larger positive numbers. As x gets bigger and bigger, raising that x to the fifth power makes that much, much bigger, still positive. So this expression is getting arbitrarily large in the positive direction, which means this is going towards infinity, okay? Alternatively, as x approaches negative infinity, again, we're approaching smaller and smaller numbers, meaning going towards negative infinity. What happens when you raise a negative number to an odd power? Does it stay negative or does it become positive? Well, if the power is odd, like 5, then it stays negative, but it gets much, much further in the negative direction. So this thing is going to be approaching negative infinity. Now, if you were to graph this function, and again, I'm going to do a very rough graph because we're only interested in end behavior, not all the local behavior. Your graph looks like this. Very similar to a cubic function, but it takes a sharper turn right there. And you can see that it's going towards infinity as x goes towards infinity, and towards negative infinity as x goes towards negative infinity, which is what these two limits are communicating, but we did it without needing to look at the graph. Okay? Okay. Let's take a look at a few more. So here we're evaluating the limit as x approaches infinity of a polynomial with more than just one term. So it's x to the fourth minus 2x cubed. There's a couple of approaches we could take here. I could look at the graph, but we want to be able to evaluate these limits without needing the graph handy. And looking at this, if I were to try and plug a very large positive number into each one of these, I would see that I have a very large number minus a very large number. It's another one of those infinity minus infinity cases that we saw previously. So remember, you can't tell just by looking at that what the function is going to be doing. So what I'm going to do instead, I'm going to factor out a greatest common factor here. This is the same thing as the limit as x approaches infinity of x cubed times x minus 2. Now think about this for a moment. It's a product of two numbers, and if x is approaching infinity, once again imagine x as being a very, very large positive number. That would mean x cubed is also a very large positive number, and it would also mean that x minus 2 is a very, very large positive number. Large positive number times a large positive number is an even larger positive number. So this thing appears to be going towards infinity based on how we analyzed this. And you could graph this function and see that that is indeed what happens. Okay? A consequence of this that you kind of intuitively justify is that when you raise something to a fourth power, it's going to grow faster than something raised to a smaller power. In fact, there's nothing unique about the 4. A number raised to a large power will always grow faster than an unknown or a variable raised to a smaller power. Okay, so in other words, this term is sort of dominating this one in the long run, and the whole function is going to be tending towards infinity. Let's take a look at another example. We want to look at the limit as x approaches negative infinity of this rational function. We've taken a look at rational functions before, and we're going to use the same strategy here. Remember what we did before is we said the limit as x approaches negative infinity of 4x cubed plus 5 over x squared minus x plus 2. I find the highest degree term in the entire rational expression. It's x cubed, right? That's the highest degree term, ignoring the coefficient, that I'm seeing on this thing. So I'm going to multiply by the reciprocal of that. 1 over x cubed, 1 over x cubed. Okay? Limit as x approaches negative infinity. As I distribute that 1 over x cubed in, I'm going to get 4 plus 5 over x cubed all over 1 over x minus 1 over x squared plus 2 over x cubed. Okay? Remember from that theorem we talked about in the last video, all of these terms, these 4 terms here, will all go to 0 as, here we go like that, as x approaches either infinity or negative infinity. So what appears to be happening is I have a constant over something that looks like a 0, right? Now technically, because it's a limit, if I'm approaching that limit, this may not equal 0 for any specific number that I plug in, but we know that the entire denominator is approaching 0. 0 minus 0 plus 0. These are the operations I'm seeing here. Okay, and as we've seen before, if you have a constant numerator, non-zero, and a denominator that's going towards 0, then this entire thing is going towards either positive or negative infinity. But which is it? How do we tell? Well, looking here, as we've seen in the previous example, the largest degree term, like what we saw up here, the highest degree term is ultimately what's going to dominate the rest of that polynomial. So when looking at this, I can kind of ignore the smaller degree terms and just focus on the 4x cubed here and the x squared here. As this denominator down here, as x approaches negative infinity, ultimately the x squared term is going to dominate these and determine what happens to this function. Any negative number squared will be positive, and so automatically I know that my denominator is going to be approaching positive infinity, or a positive number, as this limit takes x towards negative infinity. Another way of thinking about that is if you just were to graph this quadratic down here, quadratics always produce parabolas, and if the leading coefficient on that x squared term is positive, then both ends of that parabola will open upwards, which is going to be approaching infinity in either direction. So in other words, I'm getting something positive out of my denominator, but my numerator is giving me something negative, because as x approaches negative infinity, I'm cubing that, and an odd power keeps negatives negative. So I have a negative over a positive, which is a negative number, telling me that this will be going towards negative infinity. Okay. Down here I have a similar function, rational, and I'm having x approach infinity this time. I can use the exact same approach, the limit as x approaches infinity, of x squared plus 3x over 6x to the 4th minus x plus 3. Highest degree term is the one that has an x to the 4th in it. So I'm going to multiply by 1 over x to the 4th. 1 over x to the 4th. That is equal to 1 over x squared plus 3 over x cubed over 6 minus 1 over x to the 3rd plus 3 over x to the 4th. Everything that still has an x in the denominator to any power is all going to go to 0 because we're approaching infinity. X is approaching infinity here. Okay, so I have 0 plus 0 on top. This is approaching 0 over 6 minus 0 plus 0. That's 6. 0 over 6 is just 0. So in this case, our limit didn't go to infinity or negative infinity, it went to 0. Now you may be familiar with this from pre-calculus, if you took pre-calculus or college algebra or one of those things. Again, we're talking about end behavior here. And with rational functions, what we're seeing is a consequence of a more general statement we could make. If you have a rational function, which again means the numerator and denominator are both polynomials, then if the denominator has a higher degree than your numerator, which is what we have here, 3 compared to 2, that means that your rational function, as x either goes towards infinity or negative infinity, will always take you to either infinity or negative infinity. The numerator is going to win, and this thing is going to explode towards infinity or down towards negative infinity. If you have the reverse case, like we saw down here, if your denominator has the larger exponent, or the larger degree, I should say, and the numerator has a degree that's strictly smaller than the denominator, then the denominator is going to overcome the numerator and shrink that thing down to 0. And as we have already seen, which I have this example here, previous example that we've already done, if the degree of your numerator and denominator are equal, then your limit as x either goes to infinity or negative infinity will be some finite non-zero number. Okay? So that's something you hopefully talked about in pre-calculus or college algebra, even if you weren't using limit notation at that time to talk about it. All right, so that's going to be it for that. I think this is about as much time as I want to spend on this video, so I'm going to stop this one here and do this last page in a shorter part 3.